This is AP Physics, free response, question 3 for fluids. So we had a request for 2 and 3. So I haven't done 2 yet, but eventually I will do 2 a different way, I believe, than what they did. But we'll go ahead and do number 3 right now. This will be a good review of Bernoulli Equation if you need it, or if you have problems with number 3. Okay, so you should have your question in front of you if you're trying to follow along, just like in class. I'm going to have my copy right here, and I'm going to get a picture of this thing drawn up here. It's not going to be as nice as theirs, so you should look at their nice picture. Right? So I'm going to have, here's the water, and then we've got the tap thing right there. And this is open to the air. And then obviously when the water comes out, it'll also be open to the air. So one of the things you need to know when we're doing our problems with Bernoulli equation is that if the fluid has nothing but air above it, okay, the pressure, okay, at that moment then should be atmospheric pressure. Okay, 1 atmosphere, which is, you know, it's on your equation sheet what one atmosphere is equal to in terms of newtons per square meter, pascals, maybe even millibars on there. I can't remember. But anyway, so we're just going to call it 1 atmosphere for now, okay, when we're doing this, because we've got it in both spots, okay? And they said a large storage container, and the key is that this level right here is not going to change much as the liquid pours out, as the fluid comes out the spigot. So that's an approximation that you are allowed to make. I think it's got a name named after some dead person, Torricelli theorem or something like that. Probably mispronouncing that. But you can make that assumption if they ever say a very large container and then they have a small spigot, you can pretend that the liquid level is going to stay the same. All right, so we'll go ahead now and attack parts. Now we got that part out of the way. Let's go ahead and attack part A. It says, find the time it will take to fill a 1 liter flask at the spigot, okay? So we need to get 1 liter out, okay? So we need to get 1 liter out. So if I want to figure out how long it's going to take, so I want to find the time for 1 liter to come out, I need to figure out how fast this liquid's coming out, okay? I'll deal with the other part at the end, but I need to know how fast this stuff's coming out. So I'm going to start with the Bernoulli equation, okay? And I'm going to call this location 1 and this location 2, okay? And the way that I do these problems, I will call the lowest point in the problem a depth or a height of 0, okay? So I'm going to go ahead and just call this as h equals 0. So this is my h equals 0 right there. Similar to when we do conservation mechanical energy problems. Call the lowest point in your problem a height of 0. And now I'm going to write the whole Bernoulli equation out, and then we'll go from there. So pressure 1 plus 1/2 rho V1 squared, a lot like kinetic energy, right? Except instead of mass, we've thrown in a density, all right? Plus rho GH1, a lot like gravitational potential energy, except instead we're using density, equals the pressure at 2 plus 1/2 rho V2 squared plus rho GH2. Now I am assuming here that the density of this thing stays the same, and since it is a liquid, that's a really good approximation in a lot of cases. We're not going to usually have to worry about changes in density of our liquids. Okay, so let's go ahead and move through here. So pressure 1 is just 1 atmosphere. If I was actually plugging in, I would plug in the whatever 1 times 10 to the 5th newtons per square meter. But since I'm not doing that, they're going to cancel out. I'm just putting 1 atmosphere, 1 atmosphere. So that's gone. Pressure 1 and pressure 2 are gone. Okay. Now height 2, which was right here, okay, at the spigot level, height 2 I've defined to be 0. So that means that's gone because it's at a height of 0. And now we are, V1, okay, I said I can assume that the liquid level is going to not be moving because we have that big container and the small spigot. So V1, I will also assume is 0. Wow, really? Yeah, Okay. Just making sure that I agree with the key there. So lots of stuff went away. Didn't think quite that much was going to go away. I think I was thinking of a different problem, but that's great. Okay. So it's kind of like we're saying our potential energy is equal to our kinetic energy. I mean, obviously it's not that. This comes out of conservation energy ideas, but now we can go ahead and solve. So let's go ahead. We'll cancel out the rows. Let me rewrite this one time. So rho g h1 equals 1/2 rho v2 squared. So our rows will cancel out. Our density of our fluid will cancel out. I don't think they told us that, so that's good that that happened. And then g is 9.8 meters per second squared. H1 was given in the problem. This depth of the fluid or height to point 1 was given as 2 meters. So I'll go ahead and put in the 2 meters. Equals 1/2 v2 squared. So I can solve directly for the how fast it comes out of the spigot. Well, that's nice. All right, so 9.8 times 2 times 2 again, square root of all that, or half power, and I'm getting 6.26 meters per second. 6.26 meters per second. Yeah, that container, I guess that makes sense. It would come out really fast out of that small opening. Or sorry, it would come, that would actually what it comes, yeah, that's what it's got to come out at, okay, in terms of the, at V2. Let me double check and see if that's what they got. But 2 meters, I mean, think about 2 meter sticks, that's a pretty tall container of liquid, so it doesn't surprise me that it's coming out that fast. Whoops. I'm back, there you go. All right, so let's see if that's what they got. Yep, they got 6.26 meters per second as well for how fast it's got to come out at, okay? All right, so now that we know how fast it's coming out at, one of the little things that you got to be able to think about is that is we can turn that into how much comes out, okay? So if we want to know how much is actually coming out, that's how fast it's coming out. If we know how much is coming out, think about what we have to do here. We got to take our 6.2 meters per second, or sorry, 6.26. 6.2 meters per second. That's our how fast, okay? And now we got to think about, well, that's how fast it's shooting out, but now like how much, right? So we've got some sort of cross-sectional area for the opening. And in this case, I'm assuming it's a, we'll say it's a circle. Let's see here. Assume that the large cylindrical pipe of radius 0.5 that narrows to 0.2 centimeters at the spigot. So yeah, so we're going to go ahead and I'm going to do this in terms of meters per second. The key is doing this in terms of centimeters per second, so my work's going to look a little bit different from the key. But we have this opening of the spigot is 0.2 centimeters, so 0.002 meters. Okay, that's the, I don't know what I just said, but that's the radius. So that's my radius of my opening. Okay, so I need to get my area of my opening. So that'll be, the area will be pi times that 0.002 meters squared. What did I say, it was 2 centimeters? Is that what it was, 2 centimeters? Or 0.2, it's 0.2, okay, 0.2, so then 0.002, yeah, that's right, okay. So that squared times pi, so I get an area of 1.2, we'll call it 26 times 10 to the negative fifth meters squared. So that's my area of the at the end of the spigot where it's coming out. So this is our cross-sectional area, and this is the how fast. So we've got our area and we've got our how fast. Okay. Now let's go ahead and get that in terms of a volume flow rate. Okay, so we'll take the area times the how fast. So just multiplying those two numbers together. And did I write? I have not done that yet. So let me kind of just section this off a little bit. Or just get a little bit messy here. There we go. That was nice. Okay, now let me clean this up. So if we take area times V2, okay, think about our units here, meters squared, meters per second. That'll give us meters cubed per second. That'll give us our volume flow rate, or how much is coming out per unit time. So how much is coming out per unit time. So let's go ahead and figure out that volume flow rate, which is me just multiplying those two numbers that I have circled right there, okay? So let me take that times 6.26, and we're going to get approximately, let's just round it off to 7.9 times 10 to the negative fifth meters cubed per second. All right, so we got a volume flow rate And remember, our density is staying the same, so I don't even have to worry about the density part here. Remember that canceled out earlier. Okay. So now we can go ahead and figure out. We were trying to get 1 liter out of this. Okay, 1 liter out of this. So now let's figure out how many seconds that would be. Okay. So let's take our, so we have our volume flow rate. Basically, we just want to multiply by time so that the seconds will cancel out, and then get to our amount of liters. Okay, so I'm going to go ahead and take my 7.9 times 10 to the negative 5th meters cubed per second. I want to multiply that by T, so I get 1 liter. Okay, now here's the thing. 1 liter is 1,000, yeah, it's 1,000 centimeters cubed. Let me just double check here. Where's my convert? Oh, I'm already in convert, that's fine. All right, so. All right, so let me go ahead and volume. By the way, that's not, I don't think we have a conversion on our equation sheet for this, so I don't think you'd be expected to know this, but 1 liter is 0.001 meters cubed. So we're looking for 0.001 meters cubed. All right, and now we can solve for T. So we take that 0.001 divided by 7.9 times 10 to the negative 5th. And I'm getting, wow, no, that's not right. Oh, I see what I did. 0.001 divided by, how about some parentheses? 7.9 times 10 to the negative 5th. There we go. And we get a approximately 12.7 seconds for how long it would take to get that liter. They got 12.6, we're close enough. So that would be our time to fill that out. Okay. So since they were asking me for how long it takes to fill something out, I want to know how fast it's coming out at, so I can get the volume flow rate, so how many meters cubed per second, multiply by how many seconds, or solve for how many seconds this takes, multiply by the time to get the how much stuff that you want. Okay. All right, and you can do that with dimensional analysis, or you can be a little bit more formal with the flow rate stuff right there. All right, so that was part A. That was part A. And again, don't worry about this 1 liter is 0.001 meters cubed. They should give you something on that if necessary for the test. Okay, now let's go to part B. So part B asked us for the speed of the fluid as it enters the tapping device. Well, this is a heck of a lot simpler. Okay, so they have this picture, the tap enlargement, where they have a picture that looks something like this, like that. And they say that from here to here is 0.2 centimeters, and from here to here is 0.5 centimeters. So we were just dealing with 0.5 centimeters. We were just dealing with this a moment ago, where it was coming out, where it had air above it, so it was atmospheric pressure. Now we're looking at, oh, hey, we know everything about what's going on right here in terms of how fast in the area. We just want to know how fast is it going over here. So this is that idea of you put your finger over the end of the hose and it comes out faster. So we are expecting a slower speed here than we are here. Okay? So let's go ahead and just apply our continuity equation to figure that out. Now for this one, I'll just call this 1 and 2. So I just say A1 V1 equals A2 V2. And these are our velocities. Those are not volumes. Okay? So let's go ahead and do our area. In fact, let's go ahead. I'm going to do this fresh. I know I already have the area for one of these from above, but let's do this fresh as if this was just, we knew V2 and we were trying to figure out V1, okay? Because some stuff's going to cancel anyway. Also, in this equation, since I'm not going to plug it anywhere else, I don't necessarily have to be in base units. I just need all my units to be the same. So I'm going to go ahead and write pi R1, which is 0.5 centimeters. 0.5 centimeters squared. So that's my area coming into the spigot here on the larger end of the tap, I guess. And then equals, oh, whoops, how about a V1 there? Times V1 equals my area 2, cross-sectional area 2, which will be pi times 0.2 centimeters squared. Again, that's just the area of a circle, pi r squared, which is on your equation sheet in the math section, times V2, which I already have as, from up here, oh, that's why they left it in centimeters per second. All right, so I have it as 7.9 times 10 to the negative fifth, so I just need to, I gotta be careful when I convert, no, sorry, that was, there it is, 6.26, there we go, 6.26 meters per second. So in centimeters per second, just move the decimal over 300 centimeters, or sorry, move the decimal over 200 centimeters in a meter. So that'll be 626 down here. 626 centimeters per second. And now let's just check our units and see if everything works out here. So our pi's cancel out, our centimeters squareds cancel out. So my answer here is going to be in centimeters per second. But like I said, I'm treating this like its own little mini problem here. So 0.5 squared divided by, or sorry, 0.2 squared times 626 divided by 0.5 squared spits out 100. Let's see if that's what they got. Ah, that's funny. They converted it to meters per second, and I did this one in centimeters per second. So there you go, 100 centimeters per second, or they have, and it's actually 100, I got 100.2. They have 100, they have 101 actually, but we're close enough there, okay? All right, some of this is because we got they actually got 632 centimeters per second. We got 626 centimeters per second. So that's why this is a little bit different, but we're okay with that. So 100 centimeters per second, or if you want to go with the key, we got, of course, the 1 meter per second is fine as well. Okay. All right. So there we go with our B. Continuity equation stuff, that idea of, you put your finger on the end of the hose. If you make the cross-sectional area smaller, it should be going faster. And sure enough, we had it coming out here at 626 centimeters per second. It was only coming in at 100 centimeters per second. All right, so let's go ahead and now go to C. Here I have part C set up for us already, where we are trying to find the pressure just inside the tapping device here, so right there. So we'll be moving and we'll be at this depth in the liquid here, okay? So I've gone ahead and called this is different than the key, by the way, for this one. I have called this P2 and this P1 to be consistent with what I did before. Okay, so it's not going to match up with what's printed in the key in terms of the notation. The 1 and 2 are flipped. Okay. All right. So we're trying to find the difference between the pressure. Let me get their phrasing again here. We're trying to find the difference between atmospheric pressure and the fluid pressure just inside the tapping device. Okay. So the difference between the atmospheric pressure and the fluid pressure just inside the tapping device. So I need to take this, which is, again, is open to the atmosphere. So atmospheric pressure, the difference between this number and this number. So I'm just going to find the absolute value to get the difference at the end, okay, between P2 and P1. Okay, so I'm going to go ahead and get that number. All right, so I've set up Bernoulli equation here, and let's get rid of some stuff. So my height at location 2, I've called that an h of 0. So my h2 will be 0. Okay. Remember at point 1 here, we've got this real big container. It's large compared to the spigot, so we're assuming that the liquid here is not moving. Okay. So I'm going to go ahead and say that V1 is 0. And now let's go ahead and solve for P2 minus P1. Okay. So I'm going to go ahead and subtract P1 from both sides. I'm just going to rearrange the equation some here. So P2 minus P1 is going to be equal to rho G H1 minus 1/2 rho V2 squared. And again, we're going to find the magnitude of this. So at the end, I'm just going to, I don't know if I should call it magnitude. Yeah, I guess, yeah, magnitude, absolute value of the answer, because I don't care about the delta. I just want to know what's the size of the difference, okay? Because we're not dealing with vectors here anyway. Okay, so in terms of the pressure differences. All right. So now let's go ahead and plug this stuff in. And I guess they must have told us the density at some point. Oh, they did. Okay. So they did tell us the density. It's 1,000. That's really close to water. Okay. All right. So we've got 1,000 kilograms. How about I write 1,000? By the way, we could factor out a row here if we wanted to. I'm just not. So 1,000 kilograms per meter cubed times my 9.8 meters per second squared, times my H1, which I believe was 2 meters. Yep, so 2 meters. minus 1/2 the density of the liquid again, 1,000 kilograms per meters cubed, times V2, which is something we found prior. Oh, it does not line up with my previous notation. This is the how fast it enters the spigot at. We're looking at like right there. So that was, in that question, that was actually V1. Sorry for the somewhat switching notation from A to B to C in terms of the 1s and 2s, but if you have questions, send me an email. All right, so we're gonna have that 100 centimeters per second or that 1 meter per second. And then square that. All right, so let's see if that, and that's equal to P2 minus P1. And then we're gonna do an absolute value on that and get our final answer of something. I don't know what. It's here, 1,000 times 9.8 times 2. Oh yeah. All right, and then minus is just minus what, 500? Yeah, minus 500. So 19. Battery died. Believe that was 19,100, and then let's see if that agrees with the key. Yep, they got that many pascals or newtons per square meter. All right, let me get this back out. So 19,100. They got a little bit different, but again, their number right here is going to be a little bit different, and they're using 10 instead of 9.8. So I think we're okay with our 19. What did I get here? 19,100. 19,100 newtons per square meter, or pascals. Okay, they have. Let me just double check here. They have 1.9-ish times 10 to the fourth. So 1, 2, 3, 4. Yeah, 1.9 times 10 to the fourth. We're close enough based on some of their slightly different numbers. So there's our pressure difference, the size of our pressure difference between atmospheric pressure and the pressure at the bottom. All right. If you have questions, send me an email. This was the free response number 3, and free response number 2 is yet to come. All right, that was it.